In this video, we are going to be going over addition reactions of alkenes. We're going to be going over reactions of alkynes, and then we are going to proceed to talk about reactivity of alcohols. Let's get started by looking at the addition reactions of alkenes. So as you can see in this slide, we have a summary of the main reactions that you guys learn in first semester organic chemistry for alkenes. Not specifically the formation, which is what we just discussed, but this is how do we take an alkene and make new functional groups. So the way that the reactions are organized, as you can see here, are going to be in counterclockwise, starting at the top left corner of the slide, okay, with hydrohalogenation. Okay, so before I get started into talking about the reactions themselves, let's take note of the molecule that we have in the center of this slide. So as you can see, and I'm just going to zoom in, here we have a particular alkene. Now, we should remind ourselves that in this alkene specifically, we have carbons that are double bonded next to each other. And in order to illustrate all of these reactions, the carbon that is on the top, which I'm going to be labeling carbon A, the bottom one is going to be carbon B, are going to be substituted differently. What do I mean by that? The carbon on the top is going to be, or carbon A, is going to be bonded specifically to carbon atoms. Okay? As you can see, I'm just including the hydrogens to just complete the octets on the carbon. On carbon B, that one is bonded specifically to a hydrogen and then the carbon atom inside the ring, which is a CH2. The reason why I would like to illustrate the difference in the substitution of that central atom is because in some of the reactivities that we're going to be exploring here, it matters where the incoming groups are going to be placed. In general, in all of these reactions that are addition reactions of alkenes, understand that the reactions are going to happen at carbon A and B, meaning the carbon that are double bonded to each other. Because these are addition reactions, we are going to lose the pi bond, meaning one of those bonds in the carbon-carbon double bond, and then in its place, we're going to form new covalent bonds with atoms that are incoming into the system. So again, all of these processes, we are not retaining the carbon-carbon double bond, we're losing the pi bond, and in its place, we're forming new covalent bonds with the incoming atoms that are coming into the system. So let's get started with the first reaction, which is hydrohalogenation. In the hydrohalogenation reaction, which as you can see I labeled as number 1, what we have specifically is that we have our alkene reacting with HX. I'm just going to underline it. That's our reagent. In HX, as you know, X stands for halogen, and it could be any of the ones that are in group 7A in the periodic table. Now, as it is said in the parentheses for reaction 1, HX to an alkene is actually a Markovnikov addition, okay, of those incoming groups. So in hydrohalogenation, one carbon is going to get a hydrogen, the other carbon is going to get the halogen. Markovnikov addition states that the H will bond with the carbon atom with most H's. So when we look here at the labels that I placed, we can see that the incoming H, which is here, bonded to carbon B because it has the most hydrogens directly attached to itself. Okay, so that's the first reaction. Let's move on to the second one. In the second reaction, which I'm highlighting right now, and again the reactions are placed counterclockwise, we have hydrohalogenation, but this is anti-Markovnikov. So what this means, in an anti-Markovnikov fashion, then the H will bond to the carbon with least number of hydrogens. And again, if I zoom in into the reactions, you can see that even though it's not illustrated, I'm just going to write it here. The hydrogen bonded to carbon A, which is the carbon atom that has the least number of hydrogen atoms directly attached to it. Okay. Let's continue. The next reaction that we have is the acid catalyzed hydration, or the oxymercuration demercuration reaction, which, as you can see here, is reaction 3. So there's 2 reactions on reaction 3. Okay, so understand that in this one, the product of each of those reactions is going to be an alcohol. So the reaction for the acid catalyzed hydration is just reacting that alkene with H3O plus. The reaction oxymercuration demercuration is, as you can see, has 2 steps. Okay. Whenever we have a reaction that has 2 steps, remember that the number 1 and the number 2 must be written. Now, the important thing to remember of this reaction is that this reaction is a Markovnikov addition. In this Markovnikov addition, okay, I'm just going to write it right here in the corner. For number 3, we have an H coming and we have an OH that is going to be added to the carbons that used to be double bonded to one another. Okay, and as you can see, because there's a Markovnikov addition, the carbon with the highest number of hydrogen, which is carbon B, is the one that got the incoming hydrogen. On reaction number 4, we have hydroboration oxidation. In hydroboration oxidation, similar to the previous reaction, is going to be reproducing an alcohol. Okay. And one of the things that is not illustrated here is the hydrogen that was incoming in the process, but I just decided to write it in. One of the most important things to remember about hydroboration oxidation is that in this case, this is going to be an anti-Markovnikov addition. Remember, similar to reaction 3, we're going to have an H and an OH. And because hydroboration is anti-Markovnikov, the carbon atom that is attached directly to the most hydrogens will be receiving the incoming OH. And then the other carbon will be receiving the H. In the next reaction, as you can see, we have hydrogenation. And just like the name implies, here our reagent, let me just highlight 4, which is the hydroboration. So hydrogenation, which is reaction 5, which I highlighted a few moments ago. Remember, hydrogenation means that we're adding hydrogen to our alkene, which means that each one of the carbon atoms in the carbon-carbon double bond will receive an H. In the next reaction, which is reaction 6, we have bromination. Here, each of the carbon atoms in the system is going to receive a bromine. And understand that here, the addition of that bromine is going to be anti. What that means is that what we have is that these bromines are going to come up in opposite sides. As you can see illustrated in the slide, one of the bromines is placed in a dash, the other one is placed in a wedge. And because of the mechanism of the reaction, we're also going to be creating an enantiomer. The next reaction that you guys need to be familiar with is the halohydrin formation, which is reaction 7. Halohydrin formation means that the groups that are incoming into the system is an OH. And in this case, because our halogen is Br2, is going to be a bromine. Notice that in this reaction, Specifically, the bromine is added to carbon B, meaning the carbon that has the most hydrogens directly attached to it, and then the OH is going to be attached to carbon A, the one that has the least number of hydrogens directly attached to it. Also notice that this reaction has an anti-addition, meaning that the OH and the Br are going to be on opposite sides of each other, and we're going to have the formation of an enantiomer. I should specify that the En stands for enantiomer. Next reaction that we have on the slides is the anti-dihydroxylation reaction. And in the dihydroxylation reaction, which is reaction 8, what we have is that we're going to add in that carbon-carbon double bond is an OH to each of the carbons that used to be double bonded. And if it's an anti, that means that they're going to be on opposite sides of each other. That's why one is in a wedge and one is in a dash. And you can see that this is another reaction in which we have two steps, step 1 and step 2. We have the syn dihydroxylation reaction. Again, similar to reaction 8, each of the carbon atoms that used to be double bonded to one another are going to receive OHs, but in this case, if it's a syn dihydroxylation, then they're going to come in both sides. That's why you have the enantiomer, either both pointing up like in wedges or both pointing down in dashes. It's just that the ones in which the OHs are pointing down is not present. Now, when it comes to reaction 9, as you can see, we have two sets of reagents that can accomplish this. And the last reaction that you guys need to be familiar with when it comes to reaction with alkenes is going to be ozonolysis. And an ozonolysis is the first reaction in which we are actually going to be cutting both of the bonds in the alkene. Okay? And in this reaction and ozonolysis, what we are going to be forming specifically is carbonyl functionalities. So let me just highlight them in different color. Carbonyl means a carbon double bonded to oxygen. Carbon double bonded to oxygen. So in essence here, this is the first time in which we are going to cleave not only the pi bond, but the sigma bond. And at the end, we're going to be placing oxygens, okay, that result in the formation of carbonyls. Now, notice that in ozonolysis, the substituents that are attached to carbon A and carbon B do not switch. So if I label which one is carbon A and carbon B in this ozonolysis reaction, okay, let me just zoom in. Specifically, this is going to be carbon B, and this is going to be carbon A. This is this bond. This is this bond. And these are the reactions of alkenes. Let's move on to talk about the reactions of alkynes. Similar to what I just mentioned in the reactions of alkenes, we have a wide array of reactions that we have done before. When it comes to this, understand that here we have a series of reactions that are placed here. Okay, so I will go over through the 12 reactions that we have specifically here. Okay, so as you can see, reaction number 1 is going to be the elimination reaction. Okay, in this elimination reaction, which I'm just going to highlight, okay, the bond is where we have the formation of an alkyne. So if we have a haloalkane, okay, that has two halogens on one carbon, which they can be on the same carbon or they can be on different carbons, through the process of an elimination reaction, you can produce an alkyne. Understand that that process is 2 steps. The second type of reaction that we have here, as you can see, is hydrohalogenation. And here we're going to be utilizing 2 equivalents. So if we have an alkyne and we reacted with excess, that's what X and S mean. So this means excess of one of our acids that contain a halogen. Understand that that's how you're going to be forming a dihalide, but both halogens are going to be sitting on the same carbon. Okay. Reaction number 3 is going to be hydrohalogenation with 1 equivalent. Okay. Notice that in this reaction, when we do it, what we have is an alkene that only has 1 halogen present at one of the carbons that used to be double bonded to one another. Reaction number 4 is the acid catalyzed hydration of an alkyne. As you can see, the reagents that we have there is HgSO4, H2SO4, and water. In this reaction, we are going to be producing a ketone, okay? Specifically in the reaction. On reaction number 5, which is hydroboration oxidation of an alkyne, this is a reaction that it is 2 steps. We have that alkyne and we're going to be producing an aldehyde. When it comes to reaction number 6, this is halogenation. This is 1 equivalent of our alkyne. As you can see, we are going to be using 1 equivalent of X2. Remember, X equals the halogens, and they're going to be part of group 7A. In this case, similar to what we saw previously, we're going to be adding to the carbon-carbon triple bond, but in this case, each carbon atom is going to receive a halogen. When we do this reaction in excess, which is reaction 7, that's another halogenation, we form a tetrahalide because each carbon that used to be bonded by the carbon-carbon triple bond will receive 2 halogens. Ozonolysis can also happen at the level of alkynes, as you can see in reaction 8. And in this case, when ozonolysis happens, similar to what we saw before, we are going to be cleaving specifically at the carbon-carbon triple bond. Now, the middle alkyne that we have in this reaction is what we call in organic chemistry a terminal alkyne, because at one end it has a carbon and that carbon is bonded to hydrogen. So when the ozonolysis happens, meaning that we are going to be cleaving the 2 pi bonds and the sigma bond in that alkyne, understand that the resulting molecule is going to be at the area of the CH, it produces carbon dioxide. The rest of the molecule, instead of producing an aldehyde or a ketone, we actually produce a carboxylic acid. Remember, this CO2 is because we have a CH. So I'm just going to highlight that CH. So that I highlighted in yellow is what produces that CO2. Moving along, we have alkylation reaction. And an alkylation reaction of an alkyne specifically is going to be how we increase the number of carbons in our molecule. And in this case, on reaction 9, what we have is that we are going to make our alkyne a nucleophile, and we're going to be reacting it specifically with a primary haloalkane. And that's how we have a reaction in which now we increase the number of carbons in our reaction. So remember, this increases number of carbons in the compound. The next reaction that we have is reaction 10, which is the dissolving metal reduction. When it comes to the dissolving metal reduction, understand that in this reaction what we have is that the alkyne is going to be producing a transalkene. If an alkyne undergoes hydrogenation, is going to be producing an alkane. And in the last reaction that we have in the slide, this is hydrogenation with Poisson catalyst, which is Grignard catalyst. Notice that we are turning our alkyne into a cis alkene. Let's move along to now talk about how we prepared alcohols. Understand that the preparation of alcohols is pretty much a review of reactions that we have seen previously, because it has to do with reactions that involve addition to alkenes or even substitutions themselves. So, as you can see in the following slide, this is a review. Alcohols can be synthesized from alkenes via addition reactions. So, if we have an alkene, we can react it with acid to form an alcohol. We can react it with oxymercuration demercuration reaction, which is the second way. Or the third way is with hydroboration reaction. Notice that these reactions, as I explained in the previously in the video, have different ways in which the incoming OH will be added to that alkene. Make sure that you review that. Now, alcohols can also be prepared via reduction reactions, and there are 3 reducing agents that can be used. The first one is going to be catalytic hydrogenation. And in this catalytic hydrogenation, as you can see, we are starting with a ketone. And when you react a ketone under hydrogenation conditions, it will give you a secondary alcohol specifically. We can also take a particular carbonyl functional group, and we can react it with sodium borohydride, okay? And remember, NaBH4, which is sodium borohydride, is a common reducing reagent specifically for aldehydes and ketones. The example that we have illustrated right here is specifically for a ketone. And when a ketone reacts with sodium borohydride, it is going to be forming a secondary alcohol. Notice that if you have an aldehyde, in this reaction, we're going to be forming a primary alcohol. The last type of reducing reagent that we have is aluminum hydride, okay? Sometimes aluminum hydride is illustrated as LaH. So again, this is lithium aluminum hydride. Now, that is another common reducing reagent for carbonyl groups. Specifically, this is illustrating the reduction of an aldehyde, but there's other than aldehydes and ketones, esters and carboxylic acids can also be reduced with this reagent, which we're going to be exploring soon. But in the case of an aldehyde, you form a primary alcohol. And understand that when you utilize lithium aluminum hydride, that is a two-step reaction. Okay, so the second step is going to be water. Alcohols, understand that if you have the reagents that I discussed in the previous slide, you have to be careful with other functional groups that could be affected by them. So what I mean by this is that if you have, let's say, the molecule that we have in the middle, this molecule contains a ketone and an alkene. If you put this under hydrogenation conditions, understand that molecules are not smart. Molecules will look at a functional group, and if, as long as it can react to it, it will react to it. So if you have a ketone and an alkene and you propose hydrogenation conditions for it, which I just did the check mark, understand that the ketone will go to the secondary alcohol and the alkene will go to an alkane. So both functional groups will react. Now, if you have, for example, a synthetic strategy in which you only want to take your carbonyl, aldehyde, or ketone and convert it specifically to the alcohol, then you're better off using sodium borohydride or lithium aluminum hydride. The reason is because these reagents will specifically take your carbonyl and turn it into an alcohol, and it will not affect the presence of the alkene. The alkene will not be touched because these reagents do not add hydrogens to alkene functionalities. Continuing along with the preparation of alcohols, understand that, as I mentioned previously, lithium aluminum hydride is actually a strong reducing reagent. So it not only can reduce aldehydes and ketones, as we saw previously, it can also reduce esters and carboxylic acids. Okay, so the carboxylic acid will be reduced to a primary alcohol, and understand that we need excess, okay, for them, and an ester is also going to be reduced to a primary alcohol. So understand that there's many ways to produce all of these alcohols. Lastly, we are going to be reviewing Grignard reagents. Okay, Grignard reagents, understand that they act like lithium aluminum hydride. It's just that in this instance, is going to be attacking the carbonyl group of an aldehyde or a ketone. Now, every time we use a Grignard reagent in order to prepare an alcohol, understand that we are going to be forming a new carbon-carbon bond. So we are increasing the number of carbons in our reactant. So when it comes to a Grignard, as you can see in the bottom of the slide, the Grignard reagent is this reagent that I just circled. This is a two-step reaction, and in the second reaction, the reason why we have to introduce water into the system is to protonate the O- that is produced from the first step of the reaction. So when it comes to the Grignard reagent, again, this is a type of reaction that it is mechanistically something that we are also going to be observing in many of the functional groups that we will be dealing with in second semester organic. So this is a mechanism that it is important for you guys to review.